15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello again, and thank you for joining us on this, the latest episode of Space Nuts, the podcast about space with nuts on top. My name's Andrew Dunkley, and with me, as always, is Professor Fred Watson. Hello, Fred.
You see, the problem with that, Andrew, is that space doesn't have a top.
No.
So, and because that up or down relative. Is not defined in space. So. No. Maybe the space is on top of the nuts. Who knows? But the answer is yes. I'm very well, thank you. How are you?
I'm quite well too. Yeah. In talking to astronauts, they all have different interpretations of up.
Yes, that's right.
Some of them feel more comfortable with their head pointed to Earth, and others feel more comfortable with their feet pointing to Earth. And you don't know it till you get up there, apparently.
Which way you prefer?
Yeah.
Yeah.
It's a strange phenomenon.
It would be, yeah, especially if you put the nuts on it as well.
Yeah. I don't think they'd stay there.
No, probably not.
Now, we are going to talk about a massive gas giant exoplanet with a little bit of a mystery attached to it. It's got a gap in its rings, and they don't know why. They thought they did, but now they don't think that's the reason, so it could be something else. But there's another reason for looking at this planet and potential moons, because we'll get to that. Don't want to give it away too early. And a significant gamma ray burst that was discovered earlier this year is also rather significant. I think it's the first one ever observed, if I read that correctly. And we are going to answer some questions about orbital resonances from Tony and the age of light. Bart is asking that question. That's a really fascinating question. How old is light? And he's put forward some thoughts, and we'll see if we can tackle those on today's episode. But first, Fred, let's talk about this massive gas giant. This is an exoplanet that is, we think Jupiter's big, but this is a long way to the chemist shop, this one.
So that's right. So we need to recap slightly on the story with this, because this is something that's caught me by surprise. I have to say, we mustn't let this go beyond these four walls, Andrew, but I didn't know about this. I didn't know about this planet, even though it was discovered actually by somebody I know, Matt Kenworthy, 5 years ago. So even though it was published in the journals and everything, somehow it eluded me. But yes, this is an object. It rejoices in the name of J1407b, which means it's the planet of a star called J1407, because we always stick a letter on the end, starting with B for the first planet. It's a bit odd, really. Yeah. Never mind.
Well, A being the star, I assume.
Yes, that's right. Exactly. So it was discovered by the transit method. That means the way as it passed in front of its parent star, it dimmed the light of its parent star slightly, and that allowed us to understand what. First of all, the existence of the planet, but also the fact that this planet is accompanied by an incredible set of rings that make Saturn. They make Saturn look positively weedy, I have to say.
Yeah. This is one massive, massive planet.
It is. So going back to your comment to start with, its mass. And, well, between 13 and 26 times the mass of Jupiter, which is a bit interesting because in my understanding of the stellar world, or the stellar universe, anything bigger than 13 times the mass of Jupiter is likely to be a brown dwarf.
Yeah.
Because
I remember we talked about that. So this one certainly falls within that realm.
It does. And indeed, in the earlier paper, the one that was published 5 years ago, the authors do actually suggest it could be a brown dwarf. And a brown dwarf star is, the definition is, and the reason why it's all about 13 times the mass of Jupiter, is if you've got an object bigger than that, the temperature it raises through gravitational collapse in its core is enough to start something called deuterium burning, which is a relatively low level nuclear process. It's not the nuclear fusion that powers the sun, and so the amount of energy it gives off is very, very small. We do know, though, that Jupiter itself actually radiates more energy in the infrared than it receives from the sun. So in a sense, Jupiter is also not quite a star, but something that's a little bit, it's not a dead world by any means. So this object, whether it's a planet or a brown dwarf, the thing that makes it really interesting is this gigantic set of rings around it, which are actually, well, their distance, they extend out to 120 million kilometers, or about 75 million miles from the planet to the outer edge of these rings.
So they would almost reach Earth if they were surrounding our sun.
Exactly. That's exactly right. If you put them around the sun, they will be well on the way to the Earth. We orbit at 150 million kilometers from the sun. So these are sort of, 3/4 of the way there, really.
Yes.
And that is just amazing. They were discovered by the same transit method that the planet was discovered by. So this dimming as the rings themselves pass in front of the star, you can untangle all the details of that and model what you see. And it was this paper 5 years ago that recognized that it's got this enormous set of rings, which actually are quite opaque in places as well. You know, they actually absorb something like 95% of the light of the star coming through them. So why is this object in the news again, apart from the fact that it is quite astonishing? Because another paper has appeared recently. Once again, it came actually from a UK-based astronomer based at the University of Lincoln, and it was published in that great journal of the British astronomical world, the monthly notices of the Royal Astronomical Society, which is actually one of the leading journals in the world. And I, too, have published papers in there from time to time.
Nice.
A long time ago, at least for a first author paper. The journal paper talks about modelling that has been done on this ring system, because what is known is that roughly halfway out, there is a really significant gap in the rings of this world. And a gap like that in the rings of Saturn, for example, is something we know occurs because of the presence of a satellite, a moon, sometimes outside the ring system, but in resonance with the rings at that point. Again, something we'll come to a little bit later on in this chat. But usually a gap in a ring system is symptomatic of there being a moon involved, either a big moon outside the rings that's sort of creating a gravitational gap, or sometimes a tiny moon within the rings, and that's certainly true in Saturn's case. There are moons within the rings themselves which create gaps. However, it seems that this is not the case, as you said. Something else is causing this gap, because the simulations that have been done in this new work suggest that really nothing like one of these moons would actually create a stable gap in the ring system. Very odd. When you see a gap like that, the first thing you think is, well, is there a moon somewhere doing it? And then the author of this paper, Phil Sutton, University of Lincoln, he's done lots of simulations and comes to the conclusion that there isn't one. That basically there is no moon that fits the bill. It is possible that there is a moon that's actually within the rings themselves that could do it. As I said, we find those in the rings of Saturn, but that is something that has not been investigated by this researcher. So I think it's a story that is still ongoing. But of course, the reason why we're all interested in moons of these worlds,
yes,
is because they might offer somewhere where life could occur.
Yeah, because the rocky planets in the Goldilocks zone are only part of the story for the potential for liquid life liquid water and therefore the potential for life. We can't say absolutely water means life anymore after last week's discussion. But a lot of these moons that orbit gas giants are getting a different effect outside the so-called Goldilocks zone and can have liquid water.
Yeah, that's right. And it's actually the gravitational pull of the parent body itself. So if you've got a planet with a moon going around relatively close by, it's being compressed and tugged and pulled and pushed by the gravity of the planet, and that tends to heat the interior of moons. And the classic example of that is Io in Jupiter's system, the nearest of the four bigger moons to Jupiter, which is the most volcanically active body in the solar system because of its proximity to the planet. Now, something where you've got rings that extend, 3/4 of the distance from the Earth to the Sun, that's getting a long way from the parent planet, even though it's a really beefy one. If it does weigh 20, or if it does have a mass of 26 times the mass of Jupiter, that is very significant stuff, and it would have a significant gravitational effect on its any moons that it might have. So, it's an interesting speculation. Who knows what we might find one day on the moons of these gas giants.
Yes, and I suppose if it's got an ice moon or two orbiting, the potential is like we have in our own solar system, that they may have liquid oceans below their surfaces. There are all sorts of possibilities.
That's right, absolutely. So,
but the mystery remains as to the gap in the rings, but it may be a moon we haven't seen that's within the rings itself.
That's the bottom line.
Yes, all right. We will watch with interest. There may be more on J1407b in the future here on Space Nuts.
Roger, you're loud and clear here also.
Space Nuts.
Now, once again, I'd like to send out a big thank you to our patrons for supporting our podcast. You're going to start noticing bonus material popping up on the Patreon page. So if you would like to be a part of that, all you have to do is sign up. Go to patreon.com/spacenuts. And our patrons have been sending us a lot of questions, Fred, and we're going to start tackling some of those, and they will go directly to the Patreon page as bonus material. So patreon.com/spacenuts if you'd like to get in on that action. Now, Fred, we're going to talk about a gamma ray burst. Now, we know a little bit about gamma ray bursts. They're pretty darn powerful things. They're so powerful they can knock the skin off a custard. But this one particular gamma ray burst, a recent discovery, I believe, now correct me if I'm wrong, was the first one observed?
With this energy.
With this energy, right.
Yeah,
I knew I was close.
Yeah, you were close. That's all right. Close enough.
Close but no cigar. Although this would probably light a cigar.
Yes, it almost does at this distance. That's right. So what are gamma ray bursts? They are bursts of gamma rays. Gosh, we know how to give...
Yeah, we are adequate here.
Yeah.
As always.
Which have been observed, actually, I think it was in the 1970s when they started being observed. It's an interesting story because the gamma rays, of course, do not penetrate the Earth's atmosphere.
Which is a good thing.
It is a good thing, that's right. And back in, I think it was the 1970s, spacecraft or satellites were launched in order to monitor essentially to keep an eye on the possibility of rogue nations doing nuclear tests in the atmosphere, because a nuclear bomb in the atmosphere will give gamma rays, and if you've got a way of detecting that, then you know that somebody has broken a treaty or something of that sort. And that's why these things were first put in place. And they didn't find any in-atmosphere nuclear tests, but they did find all these things popping off in the sky. And they were a big puzzle for a long time. But we now believe gamma ray bursts are caused by actually the instant when a supernova goes off, when a massive star collapses to become a neutron star or a black hole. But the reason why it just doesn't look like an ordinary supernova is because these gamma rays are actually beamed out from the poles of the collapse. And the Earth has got to be in the right direction to get one of these beams, high-intensity beams of radiation. and they are very high intensity. So gamma ray bursts for a long time were a puzzle, but once people realized that they were probably coming from focused beams of radiation, then they became a bit more easy to understand. And as I said, that's what we now think they are. We think they are essentially released, maybe a supernova or something called a superluminous supernova, which is a high mass star as it becomes either a neutron star or a black hole. Now, that's the background.
Yep.
The story with this one, though, is that this is a gamma ray burst that was observed in January this year. Gamma rays, like gravitational wave events, are given a number that signifies the day on which the event occurred. And this one is called GRB 190114C. And that suggests it was the third to occur on the 14th of January 2019. They're picked up by spacecraft. That's how you detect them. NASA runs two gamma ray telescopes, Swift and Fermi, and there is one with I think it's a lovely name, this spacecraft. It's called the Major Atmospheric Gamma Imaging Cherenkov Telescope, and that is an acronym that compresses to MAGIC, which is
that's clever.
Yeah.
They don't often get the names right, but that one's a ripper.
It is a ripper, yeah. So MAGIC also detected this gamma ray burst. And what was the surprise with it was that it had the highest energy in gamma rays ever observed, 1 tera electron volt. Now, that's actually, just to put that in context, the Large Hadron Collider collides particles at up to 14 tera electron volts. So it's less than the CERN LHC, the Large Hadron Collider, can do, but this is pure energy. Effectively, these are photons. They're photons of gamma rays, and mass for mass, 1 photon at 1 tera electron volts contains about 1 trillion times the energy as 1 photon of visible light.
Whoa!
So it's big stuff.
That would light your cigar.
Yes, it would light your cigar as well as your face, probably. Put it in a way. So it's very high energy stuff. And that's something that has been predicted, that we should see these high energy gamma ray bursts, but they haven't been observed. And people wanted to observe them to find out what conditions actually produce these high energy bursts. If you've got the collapsing object as it turns into a neutron star or a black hole, this thing is emitting material from its poles, and it turns out that to get this kind of energy of 1 tera electron volt, the stuff must be coming out from the star at 99.999% of the speed of light, very, very fast, and that then kind of gives you an idea of why this might have occurred, why we might be seeing this highly energetic object, because the process that turns that material coming out from the collapsing star into a beam of gamma rays is when that material interacts with the gas that surrounds the star, what we call the interstellar medium. And as the beam of material being ejected from the star hits this this surrounding gas, that is when the gamma rays are created, and in highly directional gamma rays. And that's kind of the issue that has been raised by this observation of 190114C, because the follow-up observations that were made with the Hubble Space Telescope, which kind of zoomed in on it once this gamma ray event had been measured. The Hubble Space Telescope was pointed to the same direction in space, and it turns out that the gamma ray came from the middle of a pretty dense galaxy. It's a galaxy that actually has a high gas density at its nucleus, and the gamma ray burst came exactly from that nucleus. So one of the authors of the paper about the Hubble data, which is somebody who's at the is actually at a university in the Netherlands. There's a quotation from him, which says his name is Andrew Levan. Hubble's observations suggest that this particular burst was sitting in a very dense environment, right in the middle of a bright galaxy, 5 billion light years away.
Wow, that's a long way.
It is, but yeah, we can still register the power of the event. He goes on to say this is really unusual and suggests that might be why it produced this exceptionally powerful light. And another author is quoted as saying scientists have been trying to observe very high energy emission from gamma ray bursts for a long time. This new observation is a vital step forward in our understanding of gamma ray bursts, their immediate surroundings, and just how matter behaves when it is moving at 99.999% of the speed of light. Blink and you miss it, I think, is the bottom line with that. But yes, it's great stuff. It's a really nice piece of forensic science, because what's happened is people have used a whole array of different telescopes to first of all detect the gamma ray burst and then follow up on it to look at the environment from which that radiation has come.
So would it be fair to say that we really, even though we can create them if we want to blow somebody up, we don't really know a heck of a lot about gamma ray bursts? Are they sort of in the black hole genre of unknown?
Well, yes, they are. Although they're much better known than than when they were first discovered 30 or 40 years ago. I think the mechanisms by which they're produced are now sort of reasonably well understood. There will be models made of the kind of, this burst of matter that is going at these what we call relativistic velocities. That's velocities that are not too far from the speed of light, basically piling into the material around the object, and that's where the radiation comes from. And I think that's a process that is fairly well modeled by physicists, but you've got to observe it in order to know that it works.
Now, you said the naming of these is based on the date, and this one is GRB 190114C. So it sounds like these are happening at a fairly regular rate.
Yes, they are. They are relatively frequent. That's right, because that suggests that there were 3 on one day, which I think is probably the case.
Gee whiz, that is, yeah. And when you compare that to other events in space, that is quite unusual, I suppose.
Well, I mean, the other, I guess, one thing that they compare with, and these are the fast radio bursts, which actually are seen in the radio spectrum. They're much faster than the gamma ray burst. The fast radio bursts only last for a millisecond or so. Also, very highly energetic processes. It is thought that when we've got our detection capabilities, properly honed and properly tuned up, we'll discover one of those every day as well. They've been fairly elusive until now, but we're really only just learning how to detect them.
I suppose with all new discoveries, once we've made the initial discovery, we start looking for more, and that's why we suddenly start finding ways to discover more and more of these things, like exo-asteroids and things like that, which we've now found more than one of. The Space Doogie was the first, but we've had another one since, as far as I am aware. So,
which is a
plenty more to learn. But this has been rather fascinating. I can't get over the speed of the burst. It's just that's incredible. Given that we're going to be talking about the speed of light and the age of light shortly. You're listening to Space Nuts. Andrew Dunkley here with the great Fred Watson.
3, 2, 1.
Space Nuts.
And Fred, I'm very pleased to see that our push towards 1,000 followers on YouTube is gaining momentum. I actually had a message on my Instagram account from another podcast asking if we would like to work with each other to get our numbers up. So I basically became a follower of their YouTube channel, and they've become a follower of ours, and we're having a race to 1,000.
Okay.
And we're winning. And I'm not going to tell you who it is, because then you'll probably follow them too. And I'm very competitive. But we've got 721 subscribers on our YouTube channel now, which is
impressive.
Fantastic. So find us on YouTube and subscribe to our podcast there. You can listen to everything we've ever done in our entire lives from birth, or maybe just episodes of this podcast. I'm not sure which, but it's great that we're getting a big following there. And thank you if you're a YouTube follower. So many platforms these days, Fred. I can't keep up with it. But one thing I can keep up with is our questions. No, we can't keep up with those either. But we're getting a few back in here now, and this one comes from Tony, listening to Space Time today with Stuart Gary, who played your discussion about TESS and the discovery of exoplanets showing orbital resonances in interratios of 3.5 and 2.1. Fred mentioned Neptune and Pluto in our solar system. My understanding is that all planets exhibit these ratios, and he gives the list, but I'll just mention a few. Earth, Venus, 8 to 13. Venus, Mercury, 23 to 9, which is a weak resonance, apparently. Uranus and Neptune, 51 to 26, almost 2 to 1, and so on. Also, this may, my understanding is that these resonances focus to stabilise orbits over vast time spans. Also, this may be a mechanism for driving the solar cycles as the planets line up. What are your thoughts?
So on that last point about, if as planets line up in cycles, I don't think that has any effect on the sun itself. The sun orbits something we call the barycenter of the solar system, which is effectively the center of mass of the solar system, and doesn't care too much about planets aligning. So I think the solar cycles are much more intimately connected with the magnetic properties of the sun and the natural cycles within that. But just another comment on these resonances. It is a great topic, and the point is that if you've got two objects in orbit around another body, often you will get them settling into a resonance where one goes round 3 times for the other going round 2, or something of that sort. That's actually the situation between Pluto and Neptune. Pluto goes round twice in 3 orbits of Neptune. So what it means is that every 3 orbits of Neptune, it finds Pluto in the same place. And that essentially the gravitational effects of that are they're self-correcting in the sense that is a very stable resonance. It's one that lasts a long time, millions of years, if not billions of years. However, many of these resonances aren't stable. Sometimes they actually, you get momentum being swapped from one object to another, because of the resonance that actually destroys the resonance. So there are 2 different cases here, and it really depends on the exact parameters as to when, which are stable and which are unstable. Probably the easiest unstable one to envisage is a resonance of 1 to 1. Because a resonance of 1 to 1 means that you've got 2 objects sharing the same orbit. They're both in the same orbit, and that actually essentially causes an instability that basically it would eject. It would eject the perhaps the smaller body. It's that process that lets large objects like Jupiter clear their vicinity. Although it has to be said that Jupiter does have many 1-to-1 companions. They're called the Trojan asteroids. These are asteroids that orbit 60 degrees ahead of and 60 degrees behind Jupiter. But they're in stable positions. They're at what are called the Lagrange points. If you've got objects that aren't centered on the Lagrange points, then they'll probably get kicked out. So, a planet like Jupiter would have kicked out most of the things sharing its orbit.
Jupiter's a bully.
That's true. So I've always found orbital resonances an interesting topic, which is why we picked up on it. It's very interesting to look at just the asteroid belt, for example, in around between the orbits of Mars and Jupiter, and you find that there are gaps in the asteroid belts. They've been known for many decades. Actually, they're called the Kirkwood Gaps, and they correspond to resonances with Jupiter. So they're places where asteroids have been thrown out of resonance and distributed elsewhere in the asteroid belt. So some very interesting processes that go on. And basically, many thanks to Tony for raising it.
Wonderful question. It makes you sort of realise how small we are when there's such massive influence over such a great distance. I mean, I don't know what the guy around the corner's doing, but but that's how people think. I mean, we don't know what's going on around the corner of our street, but in a universal sense, there's so much going on that interacts over vast distances.
You don't know what's going on around the corner, but Pluto knows what Neptune's doing.
Yes, exactly what I'm saying. Yeah, it's fascinating. Thank you, Tony, for the question. Now let's move on to our next one. This comes from Bart in Amsterdam. Oh, I love Amsterdam. What a lovely place. So much fun. Hi, guys. Thanks for all the knowledge about astronomy you're spreading. Fred's doing that. I'm just pretending I understand. I've got two questions. As I understand it, if one would travel with the speed of light, time would stop in your experience and you wouldn't get any older. So consequently, as light travels at the speed of light, does that imply it's actually exactly the same age as when it was formed? And if you would give light a consciousness, would the background noise in the Big Bang that reaches us today consider this moment the same moment that the Big Bang occurred? Does light have an age at all? Do I make any sense? Yes. The second question is about the expansion of space. Does space expand everywhere, also in our solar system and also in my house, or let's say our own bodies? In other words, do I get bigger even though I'm on a diet right now? Leave the jokes to me, Bart. But yeah, good question. That second one we've answered before, but we'll do that again because it's such a fascinating thing. But speed of light. How old is light?
Okay. Bart, you shouldn't just give up on the jokes. Your jokes are actually better than Andrew's, so it's good.
I've still got the magic button here, Fred. Don't forget it.
Look, the thing about this is that time stops for something travelling at the speed of light. To an outside observer, time has stopped. That's the bottom line.
But to the light, you would not stop aging, I imagine. If you were capable of flying at the speed of light, you would still age.
You would.
It's just everything around you wouldn't.
No, that's right. That's exactly. As you're perceived from the outside, your outside observers would not see you aging. Because of time dilation, you would look to the outside observer as though time has stopped for you. But to you, as a particle of light or whatever else is traveling at the speed of light, time just marches on. So the answer is no. Light would not mix up the background noise of the Big Bang with the noise of teacups banging today or something like that. It's basically just the person observing from the outside who sees that apparent stoppage of time. I don't know whether that explains it, but that's what's happening.
Yeah, I mean,
it's all about
time it can be really complicated if you think about it too much, is what I find with time. And we're all used to time as we know it, but time isn't always as we know it. And as we've experienced with experiments on Earth, time is a variable, even at a minuscule level. But even in your own body, from head to toe, you're aging at a different rate. It's just minuscule.
Yes, that's right. That's because of the gravitational time dilation. What Bart's talking about here is it's basically the time dilation because of the speed you're travelling at, rather than the gravitational field that you're experiencing. But yeah, it's the answer is the same. It's all to do with your what we call a reference frame, whether you're looking as the stationary observer or whether you are the moving observer. And the moving observer just sees time going by at the same old rate.
Yes.
And that includes the particle of light.
I suppose his question about the light of the Big Bang not being any older than when the Big Bang occurred is a good question, and I suppose I can sort of move across into another realm. Does that light still exist, or is light just like everything else? It's created and dies and is renewed by various episodes in the universe.
Yes.
That's a good answer to a really dumb question.
So the light of the Big Bang, of course, we still see it as the cosmic microwave background radiation. But that light, when it hits something like the dish of or the sensor in a radio receiver, is converted into a different kind of energy, so it does cease to exist. But it's very old light. In fact, the light of the Big Bang is the oldest thing we can actually see. It's been on its way for 13.8 billion years.
So it's that old. But
It's that old.
not all light is that old.
No, that's right.
Yeah.
The light that's coming from my screen to my eyes now is really quite recent. It's only
very young.
It's about 2 billionths of a second old. That's right.
That's the point I was trying to make.
Yeah, that's right. So, second question from Bart, which is, as you said, Andrew, we've certainly looked at before. Yes, the expansion of space is really only visible on very large scales. So, on the scale of galaxies or solar systems, the space is expanding, but these things are held together in basically their current form by gravity, principally. And as far as your body's concerned, the space that your body occupies is getting larger at a very, very minuscule level. But the atomic forces that hold your body together are far more important, and that's why, even though you're on a diet right now, perhaps because of the fact that you're on a diet right now, but you're not getting any bigger. You're certainly not getting any bigger because of the expansion of the universe.
We don't live long enough to get torn apart by the expansion of the universe, basically. But your house is moving away from the neighbours, which is probably a good thing if they don't like you. But it will take a very long time for it to move an inch.
It would, yes. Well, in fact, it never will, because the force holding the Earth together is
going to keep it where it is.
Yeah.
Exactly. There you are. Thank you, Bart, for the joke and your wonderful questions. And thank you to everybody who's listened this week. And thank you for your support. And keep those cards and letters rolling in. Of course, if you want some bonus material, we will be providing that bit by bit on our Patreon account, patreon.com/spacenuts. If you'd like to hear more, you can do it that way. Fred, as always, thank you so much. It's been a great pleasure.
Yeah, it's been a pleasure to talk to you too, Andrew. And
well, that's a change. But anyway.
I look forward to the next time.
All right. Thanks, Fred. Professor Fred Watson, Astronomer-at-Large. And from me, Andrew Dunkley. Thanks again. Catch you next time on another edition of Space Nuts.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes and Stitcher or your favourite podcast distributor. This has been another quality podcast production from Sites.com.